talking about are just standing still, so to speak, okay? And the first idea is Pascal's principle, and you've seen this many, many different places. Anywhere they use hydraulics to input a force on one part of the system to move another part of the system, they're using this principle called Pascal's principle. So the important thing you realize here is that if I have a fluid in a system and the system is closed, meaning the fluid is contained in the system, if we have a change of pressure, if I apply pressure on any part of the system, that pressure is also felt throughout all the rest of the liquid or fluid in the system, if it's enclosed. And that should seem reasonable to you, I think. Okay. And so they have here this notional idea of a hydraulic lift in a garage. And so we'll start with this and we'll talk about some ideas related to this. Okay. And then we'll expand it to make it slightly more complicated. How does that sound? One of the ideas here, looking at this picture, is I have this smaller piston, and this area is, I'll call it A1. And if I wanted the actual area, it would be pi r squared, right? The area of a circle. We need to be comfortable with finding the area of a circle for this chapter, actually, right? And then over here, I have a much bigger, well, or I shouldn't say much bigger, but a bigger piston that has an area of 2, A2. And if I apply, and if this is full of liquid, if these things are at the same height, what can I say about the pressure at these 2 points? Those two pistons are at exactly the same height.
Same equilibrium?
They're in equilibrium. They would have what kind of pressure? P1 would be what relative to P2?
Equal.
Equal, okay? So at these 2 points, P1 equals P2. The pressures are identical. And what's the definition of pressure? May says force divided by area. So over here, if I take force 1 over area 1, isn't that the same as pressure 1? And over here, I take force 2 divided by area 2. So I now have an expression that relates forces and areas. All right, so think about this. If I want to lift a car, which is quite heavy, right? I can't really do that myself. I can't really grab it and lift it up and say, okay, go ahead and slide the supports underneath it. We can work on it now. What we'll end up doing is putting a force on one end of the liquid, and that change in pressure is felt throughout the liquid because it's an enclosed fluid, and thus gives us a force on the other piston that will support the vehicle. And so if I manipulate this equation, it would tell me, for example, how much force do I need to put in to lift the vehicle? And I say, oops, I want to make sure I get this right. Yeah, I do. All I did here was move this A1 over to this side, and I have this in a ratio, right? So think about what this is telling me. If I have a very heavy vehicle, right, and I want to lift it, I need to apply a force at least as much as the vehicle if I want to move it, right? Yes? So this is telling me I can input a smaller force into the piston on the left to help me lift this heavier vehicle, or provide an F2 on the vehicle. And what do I know about A1 relative to A2?
A1's smaller than A2.
A1 is smaller than A2, so this is a fraction that's less than 1. So if I take this fraction that's less than 1 and I multiply it by the larger force required, it tells me how much I need to put in on the left-hand side of the liquid. So if you've ever seen a backhoe or any kind of construction equipment, they all have these long silver cylinders and hoses going everywhere. Those fluids are enclosed fluids. So when you put an input force, a smaller input force into the system, you'll notice the input cylinder is quite small and the output, which is actually moving the device, is actually quite big. So I can multiply by, I can put a smaller force in to get a bigger output. It's the basic idea. I can manipulate this any way I want to make this work. This is the essence of hydraulic assist that we get from different things. If you ever look at does anybody ever look at their brake pedals? You ever stick your head down in there and see what the brake pedal, you'll notice, has, well, it goes like this and you push on this end, right? And there's a little rod, typically, and that is a hydraulic input into an enclosed fluid, and it allows you to put a smaller force in to put larger forces on your brake pads. Okay. And if you get a leak in your hydraulic system, no longer is your input allowing you to put a larger force on the output side, because the liquid is leaking, so you're not getting that advantage of pushing that pressure all the way to the other side. Okay, and you duck. Or you put on the emergency brake, which now is a push button for my car. Does anybody have one of those weird push button emergency brakes? How do those things work if the battery doesn't work?
I don't even have that.
I don't even know. It's kind of scary. I'd rather have a mechanical emergency brake. Now, is this very realistic, what I've done here?
Well, what about the car weight or
Okay, so are you looking at this picture
second
here?
one?
Yeah, so really, I have a question. Are we often working with this idea where I put in a force here and I want to move this piston over here? Or is it more like this picture over here, where I put in a force and I'm trying to lift this piston up so the car raises up? They're actually, it's rare that these two heights are the same. So how do we account for the way that works? Okay. We'll find out here shortly. I'll show you what I mean by the babble I just did. A slightly more realistic equation. This, by the way, should be on your sheet, and this is when you have your test under Pascal's principle. Okay? All right, so I'm going to redraw this picture a little bit, and we'll analyze what's going on here if I don't get myself lost. All right, so I've got a small input piston. And this is my output piston. This is still A1. And this is still A2. But now, there's a difference in height between the two things. Okay. I do know that these two pressures are identical. Okay. So these 2 points are the same. Call this H. So now realize I've got this fluid in here that's enclosed. And how much force can I get out of this thing? That's the question. For an input. pressure here, how do I'll call that P1. Okay. Here. And then there's some pressure here, I'll call that P2. And we know how to calculate P2 based on this height difference. How do I do that?
P2 equals P1 plus something GH. I don't
Plus
remember.
rho
Rho GH.
GH. Yes? What is rho again? Do you guys remember? Density of the liquid. So, what's more dense, water or oil?
Water.
Yeah, oddly, it doesn't seem that way, but it is more dense because the oil tends to float. And we'll talk about floating here in a few minutes, but turns out that water is more dense than oil, which is kind of weird if you ever put oil in, like motor oil in your hand. It feels thicker than water, but it's really not. Okay, so how do I express P1 in another way? No, what's the definition of pressure?
Force over area.
Force over area. So I could rewrite this as F1 over A1 plus rho GH, and this would be F2 over A2 as usual, right? So now if I want to solve this for how much input force I need to move the same car, let's figure out how to do that. So I'm doing more or less the same thing but with a slight adjustment, right? How do I get F1 all by itself? Oh, that's P1. Oops, sorry. Eeks. I knew I had the wrong result. I've got to go back to there and write this properly. Sorry about that. I started this equation the wrong way. Did you notice? So get your notes right. I've got P2 over here, yes? So now I want F1 by itself. I want F1 by itself. This is algebra, right? So what do I need to do first? Subtract the rho GH. So F2 over A2 minus rho GH equals F1 over A1. You guys okay with that? All right. Now if I want F1 all by itself, remember what is the force I need to put in to the input piston to move the car? That's the question. Well, I multiply by A1. So this part looks very much the same as our previous result, correct? Run, look at your notes. Isn't this what we stopped with previously? Okay. Minus rho GH A1 equals F1. What is this result telling me?
How much force for the area one?
Why does it appear that I can put in What is this telling me? What's this result telling me?
How much liquid should
You can put in a less of a force one.
Correct. What this is telling me is, remember, if you looked at the first result, I didn't have this weird term in here, correct? I had that result. Do you see that in your notes? Okay, that was assuming the pistons were at the same level. Well, now we're assuming maybe the car's down here, and I have to put in a force to lift it, right? This is telling me I have to put in less force to lift it because of this subtraction term. And what does this represent? Go ahead, say it.
Gauge pressure times area.
Kind of, yeah. If you think about this, what is H times A? What is area times height? In general. Volume. If I take volume times rho, I get a mass. And what is M times G? Weight. Okay? So what this is telling you is if you have this scenario, I can put in less force here because the weight of this liquid is helping me already by pushing down. This height and weight of this liquid is pushing down already, so I can put in that much less force to get the same lift on my vehicle. Okay? So this is the more realistic equation. And yes, it does look like gauge pressure, kind of, times A. Yeah. So this is all consistent. This is a force. This is force. Once again, this is still A1 over A2. Okay. So now I have talked enough.